So let's begin. It's a pleasure to introduce Professor Justin Holmer from Brown University. And he will be talking for the next 3 days on a survey of blow-up for the nonlinear Schrodinger equation.
Well, thank you very much to Felipe and Gustavo for the invitation to IMPA and the opportunity to give this mini course. I have set up a web page, which is IMPA. So off of my home page, if you add the suffix IMPA, then it will take you to a page where I have the lecture notes. And that is not linked from my home page since it contains copyrighted material by other other authors. The lecture notes that I have here, I have taken certain figures from other published articles without the author's permission and inserted them into the notes. Also, I have a directory that is linked from there. In fact, I'll just show you the page. I have a directory in which I have a copy of many of the papers that I reference. So that is back here. So lecture notes and then some reference papers if for your convenience. So just put them all in one directory. But of course, that's copyrighted material. So I won't be using the slides because I tend to go too fast when I use overhead slides. So I'll be writing on the board, but I have this up now to show you some illustrations of blow-up in different physical experiments. Right, so we start here. So these two images are from experiments in Bose-Einstein condensation. Actually, why don't I start with the equation? So the equation that we'll be studying is the nonlinear Schrodinger equation. The semi-linear pure power nonlinearity. Okay, so plus, so U is the function involved here, which is complex valued, and it's defined on RD. And the case of plus is called focusing. The case of minus is defocusing. And P is the power. P is the power of the nonlinearity. And blow up, the phenomena that we concentrate on, is possible. So blow up, which we define precisely, is possible in the focusing case for P greater than or equal to 1 plus 4 over D. And in particular, that includes the case of D equals 2 and P equals 3. This is the cubic, so-called cubic NLS in 2 dimensions, and D equals 3 and P equals 2, so cubic in 3D. And this equation arises as a physical model in a lot of different settings, but two principal settings are in nonlinear optics. And so it's a model in nonlinear optics and in condensed matter physics, Bose-Einstein condensation. And in nonlinear optics, it is modeling a light beam that is moving through a Kerr medium, which is one in which the index of refraction depends upon the intensity of the beam. And in that case, the t in the equation is actually the z direction. So the so-called paraxial assumption is made, in which it is assumed that we have a light beam propagating in one direction, this is the z direction, and then some kind of ansatz is made, like that the electric field is e to the I k z plus minus omega t or something like that. And that reduces it to a Schrodinger type equation in which the dt would be dz. And there would be a dz squared, but it's assumed that that's negligible. So that's the no backscattering assumption. And so it's Schrodinger, but there's no quantum mechanics involved. In that case, the dimension is 2, because there's x, y, and then the z becomes t. So the dimension is 2, and the nonlinearity is 3. But they also consider saturated nonlinearities, which are like modifications of u squared u. So you might have u squared, but then you put 1 over 1 plus epsilon u squared, or some kind of correction like that. Right, in nonlinear, in the Bose-Einstein condensation, the dimension could be anything, actually, 1, 2, or 3. It's principally, initially, it's dimension 3, except that if you include a strong confining in 1 or 2 spatial directions, you effectively reduce the dimension to 2 or 1. And the nonlinearity is 3. So it's usually cubic in the physical models. But in Bose-Einstein condensation, we're talking about ultra-cold atoms at just a couple of nanokelvins. And it's a collection of, I don't know, a few thousand atoms that collectively, that have some collective behavior that is, and the cumulative behavior is modeled by a wave function, and u is the wave function. So for example, u squared would be the probability, the probability density for that collection of atoms. And it's also an industry right now to rigorously derive the nonlinear Schrodinger equation from the quantum many-body problem. But certain assumptions are involved, like that it should be a dilute gas and so forth. But so Bose-Einstein condensation was first predicted by Bose and Einstein in 1920s, I think, and first found experimentally in the lab by Cornell and Wieman in 1995. And so okay, so in optics, let's see, it's always focusing, but in condensed matter physics, it can be defocusing or focusing. The coefficient of the nonlinearity can be modified. And so if it's focusing, then blow up is possible. And this is an image of blow up at the bottom by, in the experiments. But unfortunately, the blow up itself is not modeled by nonlinear Schrodinger blow up. The mean field model breaks down before then, but what can you do? In one dimension, then you get solitons, and that's the top frame, and no blow up. Okay, and then on the next page, so this is what blow up, at the top frame just shows you what blow up would look like if you're just looking at the plot of the amplitude of the solution. Of course, it's getting more singular and more concentrated. The bottom is a picture of simulation of optical turbulence, which shows collapse in a saturated NLS, so that lets you include some damping if the amplitude gets too large. And then, so you have these peaks form, but then the peaks are arrested, and you have an outgoing train of circular waves after the collapse is arrested. Okay, so that's it with the slides. Let me, did I just press the red button? Is that turn it off? So turn it off and then raise the screen. I won't be going back to it. So. Thanks. Thanks. Okay, so then we begin the mathematical study of this equation. So there's a number of straightforward invariances, among them being that the mass is conserved by the flow, the momentum, which is a vector-valued quantity, and the energy. In fact, it is a In fact, it's a Hamiltonian system, so in fact, the energy is involved in the structure of the equation itself, as we'll talk about. Okay. And then, so those are straightforward conserved quantities, and then some straightforward invariances would be spatial translation, spatial rotation. Laplacian is invariant under rotations. Time translation. If you bar the equation, take the complex conjugate, then you just invert the time from plus to t to minus t. We'll undo the barring. But scaling is an important invariance. Tells us a lot about the behavior. So you have the scaling, which is that u solves NLS implies that u sub lambda, which is lambda 2 over p minus 1 u of lambda x lambda squared t, also solves NLS. Okay, and that's just because the power in front is just chosen in such a way that the action, the Laplacian gives you lambda squared popping out, the dt gives you lambda squared, and then this will also give you lambda squared. So that tells us that as far as the L2-based Sobolev norms are concerned, that h dot sigma sub c is scale invariant. Where sigma sub c is equal to d over 2 minus 2 over p minus 1. That's the homogeneous Sobolev norm. Yeah, h dot c. So that's defined via the Fourier transform. Would be to the sigma u hat at c at L2 c. Yes. And so that's just, it's like having sigma derivatives. And so when you apply sigma derivatives, you get a lambda to the sigma, and then you compute the L2 norm, and you find that you need sigma equal to sigma sub c if you want it to be invariant in lambda. Okay, so common mathematical values of P and D. All right, so if we're motivated by the physics, then we would be especially interested in these cases. So we have sigma sub c, p equals 3 and p equals 5. Because 5 can be thought of as a correction to 3. Like you can modify, you can have u squared u, but then add a u to the epsilon u to the 4u as a next order correction term. In fact, the optics model is derived just by Taylor expansion. That's where the cubic term comes from. Right. So in d equals 1, we have the sigma. Yeah. So I'm just writing down the value of sigma sub c in each case. Minus a half. D equals 2. 0. So it's 0. 1/2. 1. 1/2 and 1. So it's d equals 3, d equals 4. So this is just the value of sigma sub c in each of these cases. So sigma sub c equal to 0 means that L2 is the scale invariant norm. And we see that that occurs when d equals 2 and p equals 3. And 1d with p equals 5, so a 1d quintic case. And the 1d cubic is L2 L2 subcritical, as we say, so the scale invariant norm is below L2. And these two cases in which sigma is equal to 1 are called energy critical. It's because the energy is like the gradient that lives at one derivative. So we'll be especially interested in this case of sigma equal to 0. It's the L2 critical case in which the analysis of blow-up is the most complete. Well, still plenty of open questions, but some things are known about this sigma equal to 1/2 case. It's the d equals 3, p equals 3, also physically important, but not nearly as much. Also, since perturbative methods are available in math, we can look at the sigma close to 0. So that's also pretty well understood, although non-physical, really. But okay. So a few more invariances in conserved quantity. So there's the Galilean invariance. Which says that U solves NLS implies that e to the I x dot v, e to the minus it v squared, u of x minus 2t v, t solves NLS as well. And then v can be, that's for any fixed velocity v. So what that does for you is it gives you, if you have a solution which is roughly stationary, it gives you one that's traveling with speed v. In fact, there's the special solutions that we discuss in detail called solitary waves. We get a solution to NLS in the focusing case. So plus focusing. We get a solution to NLS of Q solves the equation that. Which I write it like that because you can see it's sort of like a nonlinear eigenvalue problem in which if you imagine Q as just being a well-localized waveform, then the Q to the p minus 1 becomes the potential, and so you have a potential well, right? Because this is then a plot of minus Q to the p minus 1, and then minus 1 is the eigenvalue. And you can have a Q sitting in that well at that energy. So that's possible to construct solutions to this equation. And they're smooth and exponentially decaying and radial with very nice properties. All right, so that is a solution, and it's called a solitary wave, or sometimes soliton is used. But it stays put. Aside from the phase rotation, it doesn't move, and then you can generate solutions that move by using the Galilean transform. And you can also scale, so you can get very narrow solitons moving at whatever speed you like, or very broad solitons. Yeah, okay. Any questions so far? So that's Galilean invariance. And Now, where does this come from? Well, you can motivate it by looking at solutions to the linear Schrodinger equation, for which there's, you can solve it by the Fourier transform and some manipulations of the Fourier transform. This inclusion of e to the I x dot v is just a shift on the Fourier side. And then you can analyze that, the result of the shift in the frequency. And it gives you that this formula will work in the linear case, and then you just check it directly in the nonlinear case, and it works there too. Okay, so I'm not going to do that. But there's another invariance called the pseudo-conformal transformation, which is probably best motivated by first looking at the linear equation. So this is supposed to be an analog of the conformal invariance for the wave equation. So this is a pseudo-conformal invariance, I think discovered by Geneva and Belo, or Tilanov if you ask the Russians. So we start with the linear case. All right, so the linear case. And you start by recalling that the Fourier transform of the complex Gaussian is complex Gaussian. So you have this formula, e to the I signum t pi over 4 over 4 pi t to the d over 2. And then we can take the Fourier transform, where we accept the function of x and produces a function of c, of e to the I x squared over 4t. And you get just e to the minus I t c squared. Okay? So that's a standard PDE exercise. And so using that, we have, so we start out the free Schrodinger evolution. Is then, okay, so it's supposed to be the inverse Fourier transform of you're supposed to take that and then do the inverse, use that notation. So it's be the Fourier transform inverse going from c to x. Would be how you solve linear Schrodinger by Fourier methods. And so you have a product and then inverse Fourier transform. You get a convolution. So you have to use this formula to, so it'll be the convolution of the inverse Fourier transform of this and the inverse Fourier transform of that. So we get from this formula on the left, e to the minus I signum t pi over 4 over 4 pi t d over 2. And then we have to convolve this e to the I x minus y squared over 4t with phi hat of y dy. So it's a convolution of this with phi hat, right? So then, yes, okay. Yeah, then you take x minus y squared and you expand it. So you plug that in there. And then what you get it's tedious to write down, but so you have e to the I x squared over 4t comes out. It's not involved in the integral. And then the rest of the stuff is e to the minus I x over 2t dot y, and then e to the I y squared over 4t v hat of y dy. Right? And then you recognize that this is saying take the well, we could regard it as inverse Fourier transform of this at minus x over 2t. And so it can be written, so that can be written as e to the minus I 1 over 4t, that's the new time, Laplacian of phi evaluated at minus x over 2t. And that's if you borrow 1 over 2 pi to the d, so yeah. 2 pi, d over 2. Okay. All right, so it's a little tricky to sift through that, but it gives you. All right, so on the left we had this, and then we ended up with a different Schrodinger propagation on the right. But there's now, so time has been inverted. T is now 1 over 4t, and there's also the 1 over t to the d over 2 in front. X is now x over 2t. But that's called the pseudo-conformal transform. And so let me restate it as follows. So if you start with uxt equal to e to the it Laplacian phi, so that what we have is a solution to the linear equation with the initial condition phi. Then if we go and set u tilde, then you let u tilde be any constant you like. It's a linear equation. Right. Then you get a solution to the linear equation again. But when we evaluate it at 0, we get the Fourier transform of the initial condition here. So that's just all I did was I used u tilde. I defined u tilde to be what I have on the right here. So then when I set t equal to 0, I don't want to read off what's happening from the formula directly. T going to 0 is making things diverge here. So instead, I look at this form. I just set t equal to 0, and it's just phi hat. So that's why it's phi hat. Okay, so that works. It's a linear equation, so I can put any constant I like there. And it turns out that this remains true if you add the critical, the L2 critical nonlinearity. So I want to add u to the p minus 1 times u, but it's 4 over d because sigma sub c is equal to 0 if and only if p is equal to 1 plus 4 over d. Okay. And then I have to add that over here. So this has to be, this claim has to be checked by hand. Except now we have to change phi hat to phi plus hat, which I'll define in a second. And C has to be taken to be 1 over 2 pi d over 2. Or it won't work. Because now amplitude, because of nonlinearity, amplitudes matter. I mean, it's not linear anymore, so it's only going to work for that particular constant C. And what is phi plus? It is the forward scattering state. So where the limit So what this is saying is that we're assuming that we have a solution U to critical NLS, and it has the property that as time goes to infinity, it's matching a linear evolution, e to the it phi plus. You can put e to the it Laplacian over here, or the negative over there. It's unitary. Provided such a phi plus exists, and certainly there are solutions to this equation where no such phi plus exists. But if it does scatter as we go t to plus infinity, then we can apply this pseudo-conformal transform and allow t to go to 0 and recover phi plus hat. And so it's, I put it as an exercise in the note to derive that from the linear considerations that we discussed. So this is, provided, this is of course provided phi plus exists. And if it doesn't, it's another exercise. If there's no such phi plus, then when you allow t to go to 0, you won't get anything. It'll have to blow up at t equal to 0. Okay, so that's how you can construct explicit blow-up solutions, is by taking global, non-scattering solutions and applying pseudo-conformal transform. So if phi plus does not exist, we would say U does not scatter. Then U tilde blows up at t equal to 0. I still have to define precisely what we mean by blow up. And the way the formula works here, it's so you assume that you have a solution U defined from 0 to plus infinity, so t is positive. Then here you want to plug in t negative in order to return something positive over here. So what you have is U tilde is defined from time minus infinity up to time 0 and blows up at time 0. And then if you wanted, you could bar the equation and get a solution from 0 to plus infinity. Some people write it that way. Okay, so for example, if you start with the solitary wave, e to the I q of t q of x. That does not scatter. So as you send t to infinity, this is not matching a linear solution, because linear solutions have to spread. And this is remaining coherent. So this is a non-scattering solution, pseudo-conformally invert, and you get the standard example of an explicit blow-up solution. Okay, any questions so far? Okay, keep track of the time. Okay. virial identity to do that, well-posedness. Actually, I suppose I should say some things about well-posedness for this equation. So by well-posedness, local well-posedness, we usually mean existence, uniqueness, and continuous dependence on initial conditions. But you have to provide a function space framework. And for this type of problem, we have, so it turns out if you restrict to P between 1 and 1 plus 4 over D minus 2. So this is where you would have the critical, that is the scale invariant sublab space would be H1, the so-called energy critical. So and we're not going to touch that problem, so we just stay in the so-called energy subcritical regime. Then we have a well-posedness. Then NLS, focusing or defocusing, is well-posed, is locally well-posed. Locally well-posed in H1. And what this means is that we can generate solutions from initial conditions in H1, which are continuous, as mappings from time into H1 of x. So it's H1 of RD. And they also have a certain space-time integrability where QR is 4p plus 1 over p minus 1, comma, p plus 1. All right, so I'll explain that in a second, but you have solutions which are continuous from time into H1 of space, and you can get such a solution starting from an arbitrary initial condition in H1, although the time t depends upon the H1 norm of the initial condition. So t has to be chosen to depend upon, say, u0 in H1 x. So here what we're doing is we're looking at plus or minus, it doesn't matter, for local well-posedness. And we're looking at the initial value problem. So u0 is specified in H1. So what we can prove is that given u0 in H1, we choose t accordingly. There exists a solution u in this function class. And moreover, it's unique in this function class, but actually for the uniqueness statement, you have to include this auxiliary space too. So you get existence in this intersection, but then the uniqueness claim is also for this intersection. That's a subtle feature of the subject. And you also get continuous dependence on initial conditions. So that is, if you look at u of t, let's say t is fixed, and then you vary u0, then u of t will vary continuously as a function of u0. All right, so this is an example of a nonlinear dispersive PDE, which is a big subject. Many other examples. And you have Felipe, who's a great expert in this, right here. And IMPA looks at all sorts of examples of, and Gustavo look at all sorts of examples of well-posedness issues for nonlinear dispersive equations. And what you want are dispersive estimates for the linear evolution. And you apply that together with the contraction principle. And the typical example of a dispersive estimate that gives you well-posedness is the Strickert's estimate, And Strickert's estimates suffice in this case too. So Strickert's estimates are the following. So Strickert's estimates. So we say that QR is Strickert's admissible if 2 over Q plus D over P is equal to D over 2. Strickert's admissible for the Schrodinger, linear Schrodinger. It's also analogous estimates for wave and KdV. So, for example, what is an example? Example would be R. This should be R. QR is equal to 4, 4 when D is equal to 2. But you need 2 less than Q less than or equal to infinity. And we also need that R should be bigger than 2. And then the lower bound here on Q equals 2. The corresponding bound for R is, shoot, I didn't write it down. Yes, it's 2D over D minus 2. And you have to exclude, so the endpoint case, so QR equals 2, 2D over D minus 2. The endpoint case is called the endpoint case. And you have to exclude it when D is equal to 2. But it can be included for higher D. That's a result from 1998 by Kiel and Tao. And then you get the following estimate. So then you get the estimates e to the it Laplacian, u0, LTQ, LXR, bounded by some constant. So this just means bounded by constant times u0, L2. And there's also an inhomogeneous version of this. This is the Duhamel representation for a solution to the inhomogeneous equation. Q tilde prime Lx R tilde prime, where QR and Q tilde R tilde are admissible. Okay. Have you seen this before? Yes. No. Okay. This is it's an estimate first proved by Strickert's in 1977. But his proof has been simplified. I think it was Ginebra and Velo, and then the most frequently referenced paper dealing with this is by Kiel and Tao in '98, and they handle this endpoint case, but they also give a systematic treatment of all available estimates. So what is key is that some time integration is used. It's not a so-called energy estimate, which would just be L infinity in time. You know, it would just be comparing the size of the solution at some time t in comparison to its initial size in the Sobolev space. That's an energy estimate. But there's integration in x and t, and as a result, it captures the so-called dispersive effect. Solutions to this linear equation, higher frequencies travel at faster velocities, and as a result, there should be some kind of spreading or smoothing of waves over time, but to capture that, you have to integrate over a whole time interval. You have to average in time, and that's why you're only going to get fancy estimates like this if you work with LTQ, where Q is not infinity. So these estimates can then be the basis of a well-posedness proof once you write the solution in integral equation form. So U solves NLS is equivalent to saying U is a fixed point of a nonlinear functional. Minus plus, I forget. Squeeze it. Yes, sorry. U p minus 1 U of S ds. Okay, it's pretty straightforward to check that this formula works, but it's a standard in PDE. It's Duhamel's formula. It's a standard thing. So you want to construct a fixed point. You show that phi is a contraction mapping on a certain complete metric space, which you take to be a ball within the function class that I mentioned. So you have to show that phi is a contraction on a ball, and you choose the closed ball in the space intersect W, so LT, by which I mean time integration up to time capital T, LQ, WX1R, so that's LXR, but also one derivative with LXR. And it'll work if in many different ways you can make the Strickers estimates work. But the easiest way to get H1 well-posedness for this equation is to take QR equal to this particular admissible pair. So basically, you take R equals P plus 1 to figure out what Q has to be from this equation. And then you estimate this functional using those Strickers estimates. And so for the first term, you'll just get an upper bounds of U0 and L2. But for the second term, you have to use this inhomogeneous version. And so if you take QR to be the pair I mentioned, and then Q tilde R tilde to be the same pair, then R tilde prime will be P plus 1 over P. So it's prime. Okay, so R prime, which is R tilde prime. So this is details are in the notes, but the dual will be p plus 1 over p. And so you hit u to the p with the LP plus 1 over p norm, and you get the p plus 1 norm to the power p. And so that so you have the same thing on the left and the right of your equation when you apply that estimate with this particular choice of q and r. So you have to do that with no derivatives at the level of L2. You also apply one derivative and do it to get the H1 version. And so a lot is, so I'm skipping a lot, but it's not really a course about the well-posedness, so I don't want to spend too much time on that. Okay, so then it's 10:55, so we could pause for 10 minutes, and then another 55 minutes, starting at 11:05. Is that okay? Thank you.